In this video, we're going to talk about Riemann sums and using those to approximate the area under the graph of a function. So let's say we have a function f of x. Right now I'm going to assume that it's positive, so it's above the x-axis. Ranges from some given x value, x equals a, to another x value, x equals b. I want to find the area between that function and the x-axis. This is usually not a simple shape that we can use geometry to find the area of, so we will approximate the area using a rectangle. And if we just use one rectangle, it's probably a pretty bad approximation most of the time, so the idea is to use mini rectangles. So here is the general approach. We're going to take our interval on the x-axis from a to b. We're going to divide that into n subintervals of equal width. We don't have to use equal width, but it'll make things easier. So let's just assume we got n subintervals of equal width. We're going to call that width delta x. Since they're all the same, delta x is equal to b minus a over n. Just for some notation, I want to label the endpoints. So the endpoints of these subintervals along the x-axis. So we start out with a on the left side. I'll call that x sub 0. And then we go delta x, that's the width of a subinterval, so the next endpoint of that subinterval I'll call x sub 1, which is a plus delta x, and then we'll add one more delta x, x sub 2, that'll take us to the next endpoint, and so on until we've added delta x n times, in which case we've reached b, and that will be called x sub n. So those x sub i's are all the endpoints of the subintervals. If each of these subintervals is relatively small, then the values of the function on that subinterval are all about the same. So if I choose any 2 points, say c and d in the subinterval, f of c is approximately f of d. I'm going to choose any value, I'll call it c sub I, any value in this subinterval from x sub I minus 1 to x sub I. The area under the graph of f on that subinterval is approximately f of c sub I times delta x. Delta x is the width of a rectangle along the x-axis, and then f of c sub I is the height of the rectangle going vertically. And since if the interval is small enough and everything in all the function values are about the same, then this rectangle fills in most of the area under the curve, and it's about right. We'll see some pictures below. So we'll do that on each subinterval, and we'll just add them all up. So the area in total from x equals a to x equals b is approximately the area of each of these rectangles for the n subintervals. This whole process is called Riemann Sum, after the German mathematician who lived back in the 1800s. If we choose the c sub I, remember c sub I is just whatever we choose from each subinterval. We had to choose one x value to plug into the function. If we choose the left endpoint of the subinterval every time, what you get is called the left Riemann sum, and I have it written out here. And you can think of it either as the sum I equals 1 to n of f of x sub I minus 1, or you can think of starting at I equals 0 and going to n minus 1 and just doing f of x sub I. So you start with the leftmost endpoint is x sub 0, and you keep going. You never quite reach x sub n because that's not the left of anything, that's the right endpoint. And then if you choose your c sub I to be the right endpoint every time, then you get what's called the right Riemann sum, and here's that summation. So this starts with x sub 1, which is the right endpoint of that first interval from x0 to x1, and it stops at x sub n, which is b. It's the very last endpoint. So very similar looking formulas. If you look at sort of this one here and compare it to the right sum, same calculations. There's just a little bit of shift of indices. So there's lots of overlap between these two. Here are some pictures of what Riemann sums look like in a small example. So we have the function x squared minus x plus 1, this parabola here. I want to go from x equals 0 to x equals 2 and find the area under that curve. So I'm going to start out with 5 subintervals, so I get 5 rectangles. So the delta x, the width of each subinterval, is 2 minus 0, which is 2, and then divided by 5, so it's 2/5 or 0.4. So my first subinterval goes from 0 to 0.4, and then from 0.4 to 0.8, and 0.8 to 1.2, and 1.2 to 1.6, and then 1.6 to 2. In this, for the left Riemann sum, in this first interval from 0 to 0.4, I choose the left endpoint, 0. I plug that into the function, which is 1, and I make the area of a rectangle based on that height. So I just put a horizontal line here, and I get a rectangle. So the width is 0.4, the height is f of 0, which is 1. And then from the next one, from 0.4 to 0.8, that interval, I choose the left endpoint, 0.4. I plug it into the function, and I get the height for my rectangle. For the next interval, 0.8 is the left side. I plug that into the function, and I make a rectangle there. 1.2 is the next left interval, or left endpoint. Plug that into the function, make a rectangle. And finally, 1.6, plug that into the function, and make a rectangle. You can see that some of these rectangles have a little bit extra area, so there's some extra blue here above the curve that I don't want, and a lot of them have extra white, so I don't want this white space. I want to fill this in. The way we're going to do that is increase the number of rectangles, and that'll fill in this white space. Here's an example of a right Riemann sum for that same function. So in the first subinterval from 0 to 0.4, I plug in the 0.4, the right side, and I make a rectangle there. The next interval, I take 0.8, that's the right endpoint, plug that into the function, make a rectangle that height, and so on. And you can see that here I kind of have lots of extra blue space, not as much white space, so the actual area is somewhere between these two in this case. In this animation, we're going to look at left Riemann sums as the number of rectangles increases. So it's the same function we started with, and I'm just going to get more and more rectangles. What we should see is the number of rectangles goes up. Each one gets thinner and thinner and thinner, so the subintervals are not as wide. That means the approximation gets better, so the function is closer and closer to being, constant on that subinterval. And you can see that the extra blue that I had up above here has started to go away. You can still see some little marks there where there's some extra overestimate. And the white space started to fill in. There's a little bit you can see there. But the more rectangles we have, the better the approximation becomes. The overestimate starts getting less and less, the underestimate starts getting less and less, and we start approaching the actual area. So that's what we're going to do. If we're approaching the actual area as the number of rectangles goes up, we'll just let the number of rectangles, or the number of subintervals, increase forever, approach infinity. So we're going to define the area under this curve as the limit, as n approaches infinity, of our Riemann sum, provided that limit exists. Now here I've just put the general Riemann sum. There's any old choice of CI. And if you choose, maybe you choose the left endpoints, and maybe I choose the right endpoints. Is this limit going to be the same? And for many functions, it is the same. It doesn't matter which points you choose. If you choose the left or the right or the middle or just some random number in between. If, in particular, you have a continuous function on your interval from a to b. So if the function f is continuous, then this limit will exist, and it won't depend on the choice of the c sub I, so it doesn't matter if we choose different things, we'll get the same answer in the end. I won't prove that, but you can find the area under continuous functions. Now those are not the only ones. Many more functions this limit definition makes sense, but continuous functions, it certainly works. Now in this whole discussion I assumed that the function f was positive, so it was above the x-axis on the whole interval from x equals a to x equals b. If that's not the case, then in this limit, some of these f values here, f of c sub I, some of those will be negative. And then you would get this quantity, f of c sub I times delta x, that's supposed to be the area of the rectangle. But if the function is negative there, then you don't get an area of the rectangle, you actually get its opposite, you get a negative number. So we could just ignore all the minus signs, that's one way to do it. And maybe if you're doing geometry, that's what you do. But in calculus, it's going to be very convenient to simply decree that things below the x-axis have negative area, and things above the x-axis have positive area. So we're departing from geometry a little bit here. Geometry does not allow negative area, but in calculus it's going to make sense. So we call this signed area. If you're above the x-axis, positive area. You're below the x-axis, you have negative area. If you have some stuff that's both above and below, then that negative and positive can cancel out. So some things might have area 0, for example, if all the stuff below is the same size as the stuff above. So your signed area might be 0, even though there's actually some region there. Geometrically, you have area. All right, so kind of distinguish between the signed area in calculus and the geometric area talked about, back in geometry. Now this whole area business is really important. It shows up in other applications as well, these limits of Riemann sums. So there's special notation for that. It's called the definite integral of the function f from x equals a to x equals b. And here's the notation. There's this elongated s. You should think of that as a long s for sum because it's the limit of this sigma sum here. All right, so this summation notation uses the Greek letter sigma, which is the s sounding one. So if you take the limit as n goes to infinity, the sigma gets stretched out into this long s. All right, so this is the definite integral symbol, and these a and b tells you what values on the x-axis you want to look at, and then you have the function that you're trying to integrate. This dx here on the end tells you the variable of integration. It's similar to the Leibniz notation for derivative, which is d over dx, if you're taking the derivative with respect to x. So that's the definite integral symbol here, and that for us means the limit of Riemann sums. That's the definition, or sort of physically, that's the signed area under the curve. Now there is a command in Sage which will compute these integrals, the integral command. This time in this video we're not going to do that. We'll save that for next time. We're just going to use the sum command in Sage to calculate Riemann sums. The sum command takes 4 arguments. So you type the word sum and then parentheses. First off is the expression that you're going to be adding up. Second is the variable that's going to change as you add up, variable of summation, the index in the summation notation. And then where that variable is going to start and where it's going to end. Make sure you declare your summation variable before you use it. So here's some examples of the sum command. First off, we have k equals 0 to 10 of k squared. So I declared the variable k, typed in the word sum. The thing I'm trying to add up is k squared. That's the expression inside the summation notation. The index variable here is k. I start at 0, I stop at 10, I run that, I get 385. Here I have the variable I, so I declared I. The sum is of 1 divided by I. The variable is I, and it ranges from 1 to 5. And that's 137 over 60. Alright, here I have defined a function f of x equals x cubed. I want to add up f of n divided by f of n plus 1. So I declared the variable n, I defined the function f, and I added up f of n divided by f of n plus 1. The variable here is n. It starts at 0 and it goes and stops at 20. And here I get a very long fraction as the answer. Remember, capital N will convert to decimal. That's roughly 13.7. Okay, here's another example. I want to approximate the area between the graph of x squared minus x plus 1, same function we've been dealing with before, from x equals 0 to x equals 2. I want to use left and right Riemann sums with n equals 5, 10, and 50 subintervals. So we showed the picture up above for 5 subintervals with left and right sums. Let's see what the actual area of those rectangles were. And I'm going to set up formulas which you can use for doing Riemann sums later if you want to. So first off, f is the function I'm trying to find the area under. A is the lower limit, b is the upper limit on the x-axis. N is the number of subintervals. Those you can, if you want to copy and paste this block of code, you can change all those numbers. The rest of it you should leave the same. So dx is my shorthand for delta x, because I didn't want to type delta x every time. That's b minus a over n. That's the width of each subinterval. I'm going to use I for my summation variable, so I declared it here. And here's the left Riemann sum. I'm going to add up f of a plus I dx. So remember, those are the values of the endpoints. When I is 0, so I is going to start at 0. When I is 0, I get f of a. That's the far left endpoint. And then I will increase by 1, and when I is 1, I'll get a plus delta x, which is the next endpoint, and so on. I stop at the very last subinterval. The left side has I is n minus 1. Now the right sums are almost the same quantity. It's the function value, that's the height of the rectangle, multiplied by delta x, that's the width of the rectangle. But to get the right endpoints, I start my index at 1. So instead of starting at f of a, I start at f of a plus delta x. That's the right endpoint of the first subinterval. And then I stop at n. That will give me f of b. So when I is n, a plus n times delta x is equal to b. That's the far right side. Okay, and it prints out here the left Riemann sum and the right Riemann sum. You can see they're not that close to each other. The actual answer is somewhere between there. Here is the answer for 10 subintervals. So everything is the same except for this line right here. I changed 5 to 10, and you can see they're getting closer together, which is good. And our actual answer is still in between here. Finally, 50 rectangles, and almost agreeing with this first decimal place, not quite. So the actual area here is 8/3, or 2.6 repeating. And you can see that the left Riemann sum and right Riemann sums are getting pretty close to that. We have almost the first decimal place. But that took 50 rectangles. That would be quite a bit of work to do by hand, if you were Riemann back in the 1800s. But for us, we could do 5,000 if we wanted to, and see that the answer does get bigger, or get better and better as we go up. Now there are better ways to approximate the area than these Riemann sums. We'll talk about those in Calculus 2. But for now, we'll just go ahead and stick with these rectangles. Let's look at an example with another function. So I want to use sine of x from x equals 0 to x equals pi over 2. I'm going to use left and right Riemann sums with 50 and 100 subintervals. The actual area is 1, which you can use calculus to figure out. But let's just look at these approximations and see what happens. So same code I have above, I just changed the function to sine. I changed the limits of integration. I'm going to start with 50 subintervals here. Now the correct answer is 1. Here's my approximation with the left sum, 0.98, and about 1.02. So they're in the ballpark with 50 rectangles. We have, I don't know, pretty good, I guess. Here's the graphs, and you can see the left Riemann sum is an underestimate. There's a lot of white space that I'd like to fill in. The right Riemann sum is an overestimate. There's some extra blue above the curve that I want to get rid of. And you can see from the numbers that the right Riemann sum is too big and the left Riemann sum is too small. Okay, how about 100 subintervals? So change into 100. Now I got 0.992 and 1.008 roughly. So closer yet, and you can see that 1 does seem to be like a reasonable answer. If I kept doing this more and more, if I made n 1,000 and 10,000 and a million, I would get these numbers closer and closer and closer to 1. And when I take the limit as n goes to infinity, the answer is 1. Here's the graph, the left Riemann sum with 100 rectangles. You can see there's not much extra white space under here. There's not much extra blue space above. So this is a pretty good approximation. And so that's what we're going to do with Riemann sums. Next time we will talk about how we can integrate using Sage.